Hello viewers, welcome to the new section of this course, Performance Improvisation. We will look at some of the topics that will be covered in this section, like performance, measuring performance, profiling, other tools, programming for performance, data structures. Now let's move to the first video of this section, performance. In this video, we will understand performance and various aspects of it in detail. Let's start with performance. The performance of a software system can be broadly defined as the degree to which the system is able to meet its throughput and latency requirements in terms of the number of transactions per second or time taken for a single transaction. Performance can be measured either in terms of response time or latency or in terms of throughput. The former is the time it takes for the application to complete a request or response loop on average. The latter is the rate at which the system processes its input in terms of the number of requests or transactions successfully completed per minute. The performance of a system is a function of its software and of its hardware capabilities. Similarly, a piece of software can be made to work better on existing hardware by increasing its performance. However, the right type of performance engineering is the one where the software is tuned for the hardware in an optimal fashion, so that the software scales linearly, or better with respect to the available hardware. Now we'll move on to the next topic, software performance engineering. Software performance engineering includes all the activities of software engineering and analysis applied during the software development lifecycle, SDLC, and directed towards meeting performance requirements. In conventional software engineering, performance testing and feedback are done usually towards the end of the SDLC. This approach is purely measurement-based and waits for the system to be developed before applying tests and diagnostics and tuning the system based on the results. Another more formal model named Software Performance Engineering, SPE itself, develops performance models early in the SDLC and uses results from the models to modify the software design and architecture to meet performance requirements in multiple iterations. In this approach, both performance as a non-functional requirement and software development meeting its functional requirements go hand in hand. There is a specific performance engineering lifecycle, PELC, that parallels the steps in the SDLC. At every step, starting from the design and architecture all the way to deployment, feedback between both the life cycles is used to iteratively improve the software quality. In both approaches, performance testing and diagnostics are important, followed by tuning the design or architecture or the code based on the results obtained. Hence, performance testing and measurement tools play an important role in the step. Now let's look at performance testing and measurement tools. These tools fall under two broad categories, namely, the ones used for performance testing and diagnostics, and the ones used for performance metrics gathering and instrumentation. Performance testing and diagnostic tools can be classified further as stress testing tools. These tools are used to supply workload to the system under test, simulating peak workloads in production. These tools can be configured to send a continuous stream of input to the application to simulate high stress or to periodically send a burst of very high traffic, much exceeding even peak stress, to test the robustness of the system. Examples of common stress testing tools used for web application testing include HTTP Perf, Apache Bench, Load Runner, Apache JMeter, and Locust. Next is monitoring tools. These tools work with the application code to generate performance metrics, such as the time and memory taken for functions to execute, the number of function calls made per request response loop, the average and peak time spent on each function, and so on. Follow that, instrumentation tools. These trace metrics such as the time and memory required for each computing step, and also track events, such as exceptions in code, covering such details as the module or function or line number where the exception occurred, the timestamp of the event, and the environment of the application. Often, external instrumentation tools are used in modern web application programming systems to capture and analyze such data in detail. And finally, code or application profiling tools. These tools generate statistics about functions, the frequency of duration of calls, and the time spent on each function call. This is a kind of dynamic program analysis. It allows the programmer to find critical sections of code where the most time is spent, allowing him or her to optimize those sections. Optimization without profiling is not advised, as the programmer may end up optimizing the wrong code, thereby not surfacing the intended benefits up to the application. Now let's move to the last part of this video that covers performance complexity. The performance complexity of a routine or function is defined in terms of how they respond to changes in the input size, typically in terms of the time spent in executing the code. This is usually represented by the so-called Big O notation, which belongs to a family of notations called asymptotic notation. The letter O is used as the rate of growth of a function with respect to input size, also called the order of the function. Algorithms with a big order of big O n square can usually be optimized to work at a lower order. We will see some examples to understand. This is the code that shows how each of these orders grow with respect to n. This is the function is used to show the constant order of n. This function is used to show the logarithmic order of n. Define x of t is used to set the linear order of n. Define xl of t shows n log n order of n. Here, highlighted function is used to search square of order n. Now this function shows 2 to the power x order n. Highlighted function is used to show factorial of order n, while this function is used to show exponential for order n. Finally, the function and graph is plotted here. Let us run the code and see how the graph looks. This graph shows how each of these orders grow with respect to n. In this video, we have seen about performance factors and complexity in detail.